Hi, I am doing part B. So part B says a variable volume with a constant cross-sectional area with a perfectly stirred tank, time varying with the inlet flow and the concentration. So we're going to derive some differential equations for this. So the first thing that we want to do is let's do our drawing of our system. So we have a tank, and inside our tank, there is a stir. So then we have a flow going out, and then we have a flow going into our system. This is going to be a Q in. We have a concentration that's coming in as well. So this is going to be a Q in as well. And then inside our tank, there's going to be a concentration. Okay. So the first thing that we want to know is that we have our dV dt is going to be our Q in minus our Q out, right? And our Q out is going to be our cross-sectional area of our drainage hole, so it's going to be AD, and then it's going to be times what we already derived, which is 2G, and then H 1/2, right? So that is going to be it. So then we have our differential height. So we have the differential height. So the differential height that's changing here is going to be based on our flow rates. So our flow rates are going to be Q in, and this is going to be multiplied by the differential change in height is going to be multiplied by the cross-sectional area. And then over here, we're going to have our Q in is going to be minus our Q out, which is our cross-sectional area, the drainage hole, times our square root of 2G H to the 1/2. And then to find, just for solve for DH, we're going to divide it by AC. Okay, so the next thing that we want to know is that our tank is changing based off of concentration and height. So this is going to be dV, going to be C and H over time. And this is pretty much what our dV is going to be. This is our volume, our concentration times our height. So we have CHD, CH, D height, right? So this is going to be our concentration in, and this is going to be multiplied by the cross-sectional area as well. So our concentration in times our Q in minus our D, our area of our cross-sectional area of our drainage hole, QH. And then to solve for D, our differential concentration of height, we're going to divide by our cross-sectional area. Okay, so something that we notice is, I forgot. So when we're thinking about our Q, what's coming out of our system? Well, we need to know the concentration that's coming out of our system. If we know that this is a well-stirred flow system, we know that our concentration inside the system is going to be the same as leaving the system. So this can just be C. So C, and then we're going to divide by the cross-sectional area of the drainage hole, square root 2G H 1/2. Okay, now when we have this, we see that dCdH over dt is just product rule. So we can do a product rule of this and then solve for our differential change in the concentration. So we have our concentration times our dH dt plus our height times our dA dt. And this is going to be CIN QN minus C D square root 2GH 1/2 all over DC. Okay, so to solve for our differential change in concentration, we're going to move over our concentration times our differential height. And we know our differential change in height because we just solve for it up here. And we just are going to plug this in and help solve for ourselves. And then we'll divide by H, and then we'll get just our DC over dt. So let's solve for it right over here. So it's going to be dc dt is going to equal 1 over h. And then we're going to have CIN, the concentration in, times the flow going in minus our concentration inside the system times our differential of our cross-sectional area of the drainage times the square root of CDH all over AC. And then we're going to have subtract our concentration times our differential height dt. And then when we solve this in Python or code laboratory, we're going to plug this into it. So now we have all the parts that we're going to need for doing our code. So we're pretty much good. So, okay, I am doing part B2. So we're going to use the function IVP, solve IVP to solve this. So first thing that we want to do is let's import NumPy as P. And then from SciPy dot integrate, because we're going to be integrating our differential equation, we're going to import solve IVP. Okay, and then we're going to be using a subplot. So from plot y dot subplots, we're going to graph the differential change in concentration and the differential change in height. So make subplots. Okay. Okay, so the next thing that we want to do is after we do our imports, we're going to bring in our constants. So the first thing is our gravity equals 9.81. And then we are going to have our, so it says here that our flow going into the tank at initial steady state. So our Q in initial is going to be 0.1. And then it says the inlet flow increases by 10%. So we're going to have our Q in is going to be multiply 1.1 times our Q in initial. Okay, and then we're going to have our cross-sectional area. Cross-sectional area is going to be 1. Our cross-sectional area of our drainage hole is going to be 0.01. And then we have our concentration. So our concentration in is going to equal, or concentration in initially is going to be 1. And then our concentration in just regularly, it's increased by 25%. So we're going to do 1.25 times our initial concentration in. And then we need to know what our CA is. And so our CA initial is going to be our C in initial because it's at a steady state. So it's going to be CA initial is going to equal our concentration in initially. So then the next thing that we want to do is we're going to make our heights initial as well. Since we did our concentration initial, we need to do our heights initial. So our heights initially are, like we did in our last equation, like we did in our last homework assignment, it was C in squared. And then this is going to be divided by our cross-sectional area of the drainage hole squared. And then we're going to do times 2 times G. Okay. And then our Q is going to be our Q in initially. Okay. So, and then lastly, we need to know when our time is going to end, because this is going to be on a time interval. We need to know when our time is going to end. So it's going to be Tn plus 2000. Okay, so next, after we know that, we need to know is, well, after we know that, we need to define we're going to define our function, which is going to be our differential volume in times differential volume and change in terms of time. So this is going to be time, and then it's going to change in volume. So our volume is going to be our height and our concentration. So we're going to do height and our concentration of A is going to equal our V. So the first thing that we want to do is, what is our Q out going to be? What is leaving our system, the rate that's leaving our system? So our Q out is going to equal our cross-sectional area of the drainage hole times 2 times G times H, and then we're doing the square root of it, right? So then after we know this, we can do our differential height. So our differential change in height is going to equal our Qin minus our Q out. So Qin minus, we need this in parentheses, Qin minus Q out, and then this is going to be divided by our cross-sectional area. So after we know that, we can solve for our differential change in concentration. So what we just derived. Differential concentration, so that's going to be equal to. So on the board it says, so we're going to multiply our concentration in times our concentration times the flow in minus our Q out, well, times our QA, right? Our concentration of A, and then times our Q out. And then this is going to be divided by AC, our cross-sectional area, and then we're going to subtract it, and we're going to multiply it by our concentration, right? So our concentration of A times our differential change in height. Differential change in height. And we already solved for that, so this is okay that we're using this. So then the last thing that we want to do is that we divided it by height, because this was a product rule. So divide by height. Okay, so now the next thing that we want is we're going to return our differential change in height. And then we're going to return our differential change in our concentration. Okay, so the next thing that we want to do is, after we solve for our differential change in volume, we're going to use our solve IDP. Solve IDP. Okay, so the first thing that we know is we need to know what the function that we're going to do. So we're going to use our differential change in volume over time. And so then we have our volume. So our volume goes from 0 to time end. And then we have our initials. So our initial is going to be our height, and then it's going to be our concentration, which we both just we already initialized those. And then the next thing that we want is we need our dense output to equal true, because we want to do this at our own time and specify what time we want these points at. Okay, so we have our dense output as true, and also we need our method. So there's going to be numerical impurities in this, so we need to use the method. Reduce to solve for this IDP. So let's look at this. So as solve says our SciPy integrate. So this is going to be good. So then we can graph this at the times that we want this to be. So let's make this equal to our resolution. So then the next thing that we want is we're going to do, we need our time plot. We need our x-axis. So our time plot is going to be np.linespace. This is going to be from 0 to our time end, and this is going to be 1,000 intervals on this. Okay, so after we have our t plot, we can solve for our resolution, right? So we can do resolution.solve, and this is going to be on t-plot. Okay. And we want this, so it's giving us two arrays, and the two arrays are going to be our height, and then it's going to be our concentration, right? So this is going to be height and then concentration, right? So this is pretty good that we know this is going to be 2. So now let's make our subplots. So our subplots is going to be make, it's going to be fig equals make for subplots. And there's going to be 2 graphs. We want one for our concentration and one for our height. So this is going to be our height. So our height, so it's going to be row 1. So rows, we're going to have 1 row, and then for columns, we're going to have 2 columns. And so then we're going to have fig dot add scatter. So our x is going to equal t, and then our y is going to equal, so we have our time is going to be our x-axis, and then our y, let's do height first, and then let's do our name, height, and then the mode we want this to be lines. Okay. And then the next thing that we know is our row. We want this to be in row 1, and then we want this to be in column 1 as well. Okay, so let me just copy and paste this over. And I'm going to do this for the concentration as well. So this is going to be CA, and then this is going to be CA, and this is going to be column 2. Okay, and then let's do fig dot update underscore layout, and this is going to equal our so it's going to be layout, and we're going to have our height is going to equal 600, and our width is going to equal 1,000. So shift enter. Okay, so we can see that our concentration and then our height level out, and they are both at a constant level out. And it looks like they're leveling out just under 6.2 on height, and then a concentration, it looks like it's leveling out at 1.25. Okay, thank you.